This is question 17 from the SACE Stage 2 Physics course companion from Subtopic 3.1, the wave behavior of light. Here we have light with a wavelength of 523 nanometers incident upon a transmission diffraction grating with 500 lines per millimeter. First, we need to calculate the angular position of the first maximum, but before we get into that, we may as well write down all the things we know and all the other calculations we need to do before we can even start. Here the question is telling us that the wavelength is 523 nanometers. That's probably worth writing down to begin with. Now 500 lines per millimeter, that tells us obviously how many lines there are per millimeter of the transmission diffraction grating. What we need is the spacing between one of those. So if there's 500 per millimeter, then we need to work out the distance between those, so that'll be 1 on 500, and since that's how many per millimeter, we need to add a scale factor of 10 to the 3 to make it per meter, and if we substitute that out into our calculator, we get 2.0 times 10 to the minus 6 meters. So yeah, this is probably the trickiest thing, because it's not something that's immediately obvious that you need to do, but it's good to get into practice of 1 on 500. If it's 500 lines per millimeter, then 10 to the 3 because it's per millimeter. We're trying to work out how many there are per meter, not per millimeter. That's why we're including that 10 to the 3. Alright, so now we can actually start doing the question. So the angular position of the first maximum, using the expression m lambda equals d sine theta, we want an angular position, so sine theta equals m lambda on d, therefore theta equals the inverse sine of m lambda on d. Now we just go through and substitute in all the things we know. So here we have the first maxima, so m equals 1, therefore theta will be the inverse sine of 1 times 523 times 10 to the power of minus 9, because it's nanometers, divided by 2 times 10 to the minus 6. And if we substitute that into our calculator, we should get 15.2 degrees. Part B is a little bit more difficult. We need to find out the highest order maximum that can be observed with this diffraction grating. So here, this process is a little bit tricky if you're not used to it. So the maximum angle we can observe is when theta equals 90 degrees. Therefore, we're trying to find the value of m such that m lambda equals d sine 90. Now, it's highly unlikely we're going to get an integer value for m, so we'll work that out once we get to it. Sine 90 is just 1, so we have m lambda equals d, therefore m equals d on lambda. Now we substitute our values in. 2 times 10 to the power of minus 6, 523 times 10 to the power of minus 9, and if we substitute that into our calculator, we get 3.82. Now that means that we don't actually see the m equals 4 maxima because it doesn't quite reach it, so we have to round down. Therefore, the highest order maxima that we see is m equals 3, because we don't quite get 4. So again, that's not too bad after all. And the hardest bit is communicating your reasoning for why it has to be 90 degrees, but that doesn't take much. And yeah, that's it. So it's not actually a very hard question, but there's a lot of tricky sort of concepts and calculations that you have to do, the implicit within the question, that it's not something that you're asked explicitly to do, like calculating the distance between adjacent slits in a diffraction grating. But aside from that, yeah, it's not too bad.